Yo, what's up, everybody? This is Mr. Nixon. Just putting together a quick video for you guys. I'm going to be posting these videos a lot more regularly, just to kind of interact with you and kind of discuss some things. Because sometimes it's just there's some things that I can write and I can put in an announcement, and then there's other things that if you listen to me say it along with the announcement, it's just going to make a lot more sense. And I wanted to do that for chapter 20. And before I get into chapter 20, let me say this. I'm currently in school as well. So, about the last lecture test, I know some people did good. Some people didn't do as well as they wanted to do. And that's understandable. We're going to turn that around. And I say we collectively, not you, but we as in you and me and the rest of us, we're going to turn that around. So if you need help, I love the post that some of you have been making on the discussion sections. You've been giving one another some really good advice. I think that the advice that some of you are giving is better than some of you think. If you haven't tried some of the advice, some of you guys have been talking about Quizlet. Some of you have been talking about making your own note cards. Some of you have been talking about the animation. Some of you have been talking about the amount of time you study and when you study. Those are very important things, especially with a class that's condensed in just 10 weeks. So talk amongst yourself, work on that. If you got ideas, bring me these ideas. Let's throw them off of one another and kind of see what we got and see what we can come up with together. So as far as my end is concerned on chapter 20, I kind of just wanted to talk a little bit about some things. I've got my monitors up and I'm looking at some things. Okay, let me just be honest. I got a list of things that I want to put on the test, and I'm looking at them now, and I'm like, okay, you know what? If I put this on the test, I want to make sure that they understand it. So that's what some of these videos are going to be about, that you're going to see posted over the next week between now and the lecture test, is getting you ready for the test and tackling some specific topics. All right, so with all that said and done, let's get to the meat of it. First and foremost, you really need to remember that when you get to chapter 20, they're kind of talking about the physics and the interaction with the rest of the body that the blood circulation is having. If you've never looked at how pipes work, then this would be a good time to kind of look at like a TED Talk about how pipes work. That would be good. There's a TED Talk, I think I posted it to you guys, I hope I did, the one about the guy who repaired his own heart, and he was repairing his aorta. And if I didn't post that, let me know. I will post that to you. You can go to TED.com, you go to the search box and just type in how I repaired my own heart. I think that's the actual name of the TED Talk. How I repaired my own heart. And he goes through the whole thing of how he's an engineer and he works with pipes all day. And the doctors were saying, hey, you're going to have to be on medication for the rest of your life. But he looked at it from an engineering problem. And he said, nah, I don't need medication. I actually need some type of physical structure. And he and his buddies together, and they used a 3D printer and created a structure that allowed his aorta to repair on its own. And now he can live without threat of an aneurysm in his own aorta. I thought it was pretty fascinating, really. So think of your blood vessels as pipes, and think about the fact that all your arteries are doing are just taking blood away from your heart, and that veins are bringing blood back, and that both the arteries and the veins have to have specific structures built into them so that they can function like that. Because arteries are going to be under a lot of high pressure because the blood just left the heart. The heart's a big pump. So when it contracts, it squeezes and it pushes this huge amount of pressure into any artery that's open. They say that if you got shot in your aorta, you'd bleed out in like 20 seconds. Seriously. Because you've got that much blood pumping out of the left side of your heart at any given moment. There's only 5 liters on average of blood in your body, and your heart's pumping 5 liters of blood through your entire body every minute. So every 60 seconds, at least 5 liters of blood is circulating throughout your circulatory system in your body. That's a lot of freaking blood. So the arteries are under a lot of pressure because all of this blood is initially coming right out of the pump. But then it goes to your capillaries the velocity that it's traveling kind of goes down. The amount of pressure that's there kind of goes down. And so when it comes out of your capillaries, the amount of pressure that the veins are working with is significantly less than there is in the arteries. So yeah, you use a little bit of blood pressure to get blood back from the veins to your heart, but it's not the same. It's only a fraction of how much pressure was in your arteries. So you have to rely on things like gravity and muscle movement and breathing to actually and to push blood back to your heart. That's why your veins have valves and your arteries don't. Your arteries have so much pressure, the force of the pressure is going to be constantly pushing blood through the arteries. But when it comes to veins, you have to have valves because there's not as much pressure, and so blood, because of gravity and things like that and resistance, blood is just going to kind of slow down and try to go backwards. And so the valves stop that blood from going backwards and just pooling in the veins. When the valves and veins begin to break down, especially in the legs, that's where people get varicose veins from. What's happened to them with varicose veins is the valve wind up collapsing. They get weak and they collapse, and the blood pools down into the veins, and it causes the veins to swell and distend and stretch, and the blood pools down in there instead of all of it going back up to the heart, which becomes problematic. So you want to try to make sure you understand pressure, understand the concept of blood pressure, understand the concept of resistance. So, resistance is just anything that, so like, for example, I'm at my real office. Usually when you're looking at these videos, I'm in someone else's office or in an adjunct office, but this is my real office with the War Machine helmet. That's my real armor back there, and this mannequin over to the side. But I've got this real big desk in here. Some of you have actually been to my office before. If I tried to push this desk, it'd be very difficult because there'd be a lot of resistance. This desk weighs a lot, and so the weight is adding to the resistance, keeping this desk from moving. Sometimes things like blood, water, just something in motion, sometimes the resistance that it's encountering is simply distance. So the longer the distance your blood has to travel, the more resistance it's going to actually encounter because of that distance. That's a normal thing. So there are terms like this, and I'll throw a few out there to you guys on Monday. Words that you want to be familiar with: resistance, pressure, things like cardiac output. You want to be familiar with things like that as well. Now, let me hit on something real quick, and people really don't like this one, and no offense, I don't blame you because it's kind of tough to grasp. I don't have my textbook in here with me right now, but there's an image in chapter 20 and everybody hates it. It's an image of, I'll show you what it looks like. It's an image of a capillary. It's just one singular capillary, and it shows an arteriole and blood flow going into a capillary, and then it shows all these pressures of things going in and pressure of things going out, and it looks like that, okay? And it has a bunch of arrows pointing of things going in and arrows of things coming out. All right, you need to know that picture. You need to know that picture, and you need to understand that picture. I can pretty much guarantee that I'm going to put some questions on there about how things get in and out of capillaries. It's important to understand that. And the reason why is not because I'm trying to be evil, but because, number one, how things get in and out of your capillaries, that's going to be on this test. It's going to be in the urinary system. You're going to need to understand it for the digestive system. You're going to need to understand it for the respiratory system, and you're going to need to understand it for the fluid, the fluid chapter, and you're going to need to understand it a little bit for the metabolism chapter. You get in the picture? You have to understand how things get in and out of capillaries. Now, capillaries are closed structures. When blood flows through an artery, it then flows into an arteriole, and then after it flows into an arteriole, it flows into a capillary bed. Capillaries are really cool little structures because they're only one cell thick. The wall of a capillary is called the endothelium, which is a fancy word for simple squamous epithelium. Simple, one, squamous or squamous, flat, epithelium, cover or wall. A wall with one flat cell thick. Something that thin, yeah, that is meant for things coming in and out freely anytime you want. And that's exactly what you have capillaries doing. Capillaries are allowing you to be able to get things in and out of the bloodstream as often as you like. So respiratory gases, oxygen is leaving the blood and going out to the tissues. Carbon dioxide is coming from the tissues and going into the blood. You got water coming out of the capillaries into the tissues. You've got glucose, you've got amino acids, you've got electrolytes, you've got waste products coming from the tissues and going into the capillaries and then leaving the tissues. That's how they throw their trash away. So it's very important to understand the concept of capillaries. Pay close attention to that image. You want to be able to conceptualize that a capillary is like a bus stop. You know, if you've ridden the bus, and I know that might sound dumb to some of you, you're like, Mr. Nixon, everybody's ridden the bus. No, they haven't. If you've ridden the bus or if you've ridden a subway train, then you know that while that train is moving, everybody's on that train. And unless your name is Spider-Man, you're not jumping out of that train and, you know, surviving and going about your business. But once that train gets to a stop, you can let things on and you can let things off. And that's capillaries, except the blood never stops moving. Things go in and things go on. It's like a train. They just get on and off, on and off. And that's the way it's built. Diffusion helps this. Vesicular transport deals with this. And there are certain pressures that help to enforce the movement of substances out of the bloodstream and into the tissues and vice versa. Now, hydrostatic pressure pushes things out of the capillaries all of the time. Hydrostatic pressure is, if you caught the word parts, hydro is referring to the water, which is in blood plasma. The liquid portion of your blood, the blood plasma, which is 92% water, it's got so much pressure, it's forcing solutes out of the capillaries and into the body tissues. So you got to remember, a lot of this stuff is dissolved in the water, in the plasma, in the blood. I'll say that again. A lot of this stuff that your cells need are dissolved in the plasma, is dissolved in the water that's in the plasma, that's in the blood. It's like if I made Kool-Aid. If I came to you and said, hey, I need a few cups of sugar. Notice I said a few, right? Because you're making real Kool-Aid. So if I said, I need a few cups of sugar to make some Kool-Aid, and I took the cups of sugar and mixed them in with the Kool-Aid powder and the water, mixed it all up and everything, and then you came back 15 minutes later and you said, hey, Mr. Nixon, I'm sorry, I forgot I needed one of those cups of sugar back. I'd just have to look at you and be like, dude, I'm sorry, man. I'm going to have to spot you some sugar when I go to the store, because the sugar is now dissolved in the water and I don't have a physical way to remove the sugar out of the water. Now, for you uber nerdy people out there, you have already thought of ways that you can take sugar out of the water, but that's using a chemical process like you're in a lab. We're talking about in the human body, and we're talking about in that Kool-Aid pitcher. At that moment in time, with just us standing there, there's not an efficient way to measure out exactly 1 cup of sugar out of the Kool-Aid. You can't do that, all right? Not without some type of chemistry going on in the back in a lab. So what winds up happening is, if I want to give you some of your sugar back, I have to give you Kool-Aid, because the sugar is dissolved in the Kool-Aid. The same thing happens in your body. If I want glucose out of your blood, guess what? That glucose is going to very possibly, wherever the water goes, that glucose is going to go as well, and vice versa, because the glucose is dissolved. That's how I got the glucose to the tissues in the first place. The glucose is dissolved in the blood, it gets to the capillaries, and then through diffusion, the glucose can diffuse out of the blood and into the body tissues. And the reason why is because there's water in your blood plasma and there's water in the tissues. All those cells out there are surrounded by water. So they're just going from water to water. It's literally going from one water medium to another water medium. So it's all gravy. That's why your body is like 70% water. That's why everybody says, oh, your body's mostly water. And that's why they're using it in horror movies and horror video games now, where they talk about the body being mostly water, because it's a transport medium. It's the easiest way for us to move solutes from one place to another. That's why it's important to stay hydrated and keep water in your body, because the less water you have, the more difficult it is for you to be able to transport nutrients and do different things like that, and get rid of waste products as well. So when I get to the capillaries, I use hydrostatic pressure to force items out of the capillaries and into the surrounding tissues. However, if I just had pressure moving one way and constantly pushing stuff out of the blood, then I would swell up like a butterbean, and I'd ultimately die, because all of my body fluids would be in my tissues and none of it would be running through my blood vessels, and it would be a very sad day indeed. So when I force that stuff out of the capillaries so that it can be a transport medium to get all the solutes out, I then in turn need to be able to bring that water back and put it back in the plasma, which is back in the blood. So I use osmotic pressure to do that. Osmotic pressure is usually referred to as colloid osmotic pressure, which is actually, or blood colloid osmotic pressure, as we like to say it, because we need to be specific about where we're talking about it. Blood colloid osmotic pressure is controlled by the plasma proteins in your blood. Notice that solutes and water will leave your capillaries and go out into the tissues, but most of those plasma proteins don't, because those plasma proteins are too big. So the plasma proteins kind of stay in the capillary while other stuff leaves. The presence of the proteins in the blood kind of trick the water and makes it think that, oh, there's this high concentration of ions, so there must be a low concentration of water, so I need to go back there. So it tricks water into leaving back out of the tissues and going back into the blood plasma, which is why the textbook refers to that process as reabsorption. Not absorption, but reabsorption. The word part re means to return. So if I'm reabsorbing water back into the bloodstream, that meant that it left through hydrostatic pressure and now it's coming back through blood colloid, which is great. That's exactly what I want anyway, anyhow. Anything that's dissolved in the water that wants to come back is more than happy and more than welcome to come back, because it's still in my body. It's not like I'm going to waste it. It's not like I'm going to lose it. It's all gravy. So that's why it's important to take care of your liver. I know you're like, where'd the liver come in from all this? Because your liver is the one that's making albumin proteins, plasma proteins, the ones who are responsible for blood colloid osmotic pressure. Your liver makes those plasma proteins. Those plasma proteins go in your blood. They help to maintain blood colloid osmotic pressure. So an individual whose liver is breaking down thanks to cirrhosis of the liver, they are struggling, because now that cirrhosis is destroying the cells in the liver that are responsible for making the plasma proteins. Therefore, you're not maintaining blood colloid osmotic pressure the way that you should. And so when water goes into your tissues, it's becoming very difficult to pull that water back out of the tissues. And you'll notice that that patient swells up very easily. Yeah, not good. Okay. So I'm going to stop this right here. This should kind of give you an introduction going to look at that image. You got any questions about the image, you know where to find me. Shoot me an email real quick, ASAP. Anybody that, I see some of you guys taking micro or taking other classes, stop by the office, let me know, give me a call, whatever, and we can talk and we can chat it up. All right. Look forward to talking to you on the next video. Peace.